In this video, we will discuss describing solutions as being either acidic, basic, or neutral, and we're going to talk about the pH scale. Now, in previous videos, recall that water is amphoteric, meaning it can behave as both an acid and a base. What this means is that according to both proton transfer and electron transfer, water is going to have the ability to interact with itself. When water is a base, its conjugate acid is hydronium, H3O+. When water is an acid, its conjugate base is hydroxide. One water molecule can transfer proton to another water molecule. The same process involves electron transfer as well. So remember, according to our Lewis base theory, our Lewis bases are going to donate electron pairs, and my water molecule has electron pairs that it can donate to a hydrogen, forming a bond. So this bond forms, this bond breaks. So when we form that bond to the hydrogen, we're going to get our hydronium, the H3O+. We break the bond to hydrogen, we're going to get hydroxide, our conjugate base. So the first water molecule donates an electron pair. As it does so, it's also accepting hydrogen from the other water molecule. So it's both that Lewis base and that Bronsted-Lowry base. The second water molecule accepts the electron pair and in turn donates the hydrogen, making it an acid. Also notice that we used those arrows indicating a reversible reaction. We used our double arrows. Recall that all reversible reactions are going to reach an equilibrium. So we can write the interaction of water with itself, which we're going to call the autoionization of water, in which we have water molecule interacting with a water molecule to produce hydronium and hydroxide. Now, going back to some equilibrium review, remember we can describe our equilibria as being either heterogeneous or homogeneous, and that depends on our phases. This particular equilibrium is going to be heterogeneous. We have different phases. We've got liquid in the reactants, we've got aqueous in the products. Now, if I've got a reaction that goes to equilibrium, remember for any of those reactions, we can write a K expression. So K will equal concentrations of my products, each raised to their coefficient. So my hydronium raised to its coefficient of 1 times my hydroxide raised to its coefficient of 1. And then we would typically divide by our reactant concentrations. However, notice that our reactants are liquid. And remember that our liquids we're going to omit from our K expression. So, since both reactants are liquid, they're not going to show up in our equilibrium expression at all. So our K just equals the concentration of the hydronium times the concentration of the hydroxide. So K for the autoionization of water is called Kw. It is always equal to 1 times 10 to the negative 14th at room temperature. Remember that K, no matter what kind, so we've got a different subscript here. We've got a Kw rather than a Kc or a Kp, but it always indicates the same thing. It's indicating the extent of our reaction. My K here is going to be very small. 10 to the negative 14th is a small K. If we have a small K, remember that our equilibrium favors our reactants. And when that's the case, that means that at equilibrium, we have very few products. And so that means we would expect that the concentrations of those products, the hydronium and the hydroxide, to be very small. Now, if we assume our initial concentrations of a hydronium and hydroxide are both 0, which is acceptable, they're products. We would assume we have no products if our reaction hasn't occurred yet. Based on this, we can set up our ice table. So we did ice tables in previous chapters. We're going to set that up. So we're going to take our equation, our 2H2O, producing our hydronium and our hydroxide. So we're calculating equilibrium concentrations. This is how we know to set up an ice table. Anytime we're calculating equilibrium concentrations, we need an ice table. So we're going to set up our rows I, C, and E. Now, because water is a liquid, it doesn't matter how much of it we start with. And my products, we know, are initially 0. So then we're going to set up the rest of our ice table in terms of X. And so we know that any reactants are going to decrease by some X amount related to their coefficients. And my products are going to increase by some X amount, again related to their coefficients. So that equilibrium, we would have our initial minus X, but since water is a liquid, it doesn't really matter. So we're just going to X that out. My hydronium would start at 0. We're increasing by X, so we have some X amount at equilibrium, and we have some X amount of hydroxide. Now remember from previous exercises that to solve for our equilibrium concentrations, we're going to plug that equilibrium line into our K expression. And so remember that K, which we said we're going to call it Kw, is equal to the hydronium times the hydroxide. So at equilibrium, my hydronium is X, my hydroxide is X. So I have that X squared equals Kw. And we just said Kw is always 1 times 10 to the negative 14th at room temperature. So I can solve for my X, so I'm going to take the square root of both sides. And I'm going to get that X is 1.0 times 10 to the negative 7th. So plugging my X back into my ice table, my hydronium is 1.0 times 10 to the negative 7th at equilibrium, and my hydroxide is 1.0 times 10 to the negative 7th molar at equilibrium. So this is going to be true as long as I have a sample of water at room temperature. These will be my hydronium and hydroxide concentrations. And notice that they are very small. We said we had a small K. We would anticipate that we should have very small amounts of products. Now, when we compare these two concentrations, note that they are equal. So in a sample of water, the hydronium concentration equals the hydroxide concentration. We're talking about a sample of pure water. So in a sample of pure water, the hydronium equals the hydroxide, which equals 1.0 times 10 to the negative 7th molar. A solution is described as being neutral when the hydronium equals the hydroxide, which again equals 1.0 times 10 to the negative 7th molar. Now, an acidic solution is going to be one in which whatever we're adding something to water and the hydronium concentration increases. So, if a neutral solution contains 1 times 10 to the negative 7th molar and an acidic solution increases the hydronium, how's an acidic solution compared in terms of hydronium? And so what we find, because we're increasing the hydronium, in an acidic solution, the hydronium concentration will be greater than 1 times 10 to the negative 7th. Now, we've got water. Water interacts with itself. It reaches an equilibrium where we have these set amounts of hydronium and hydroxide. We add an acid to water. It increases the hydronium, making it an acidic solution. Now, we have just added a stress to our equilibrium. And in order to maintain a constant Kw, if we increase hydronium, we're going to have shifts in our equilibrium. So we're going to see that something happens to our hydroxide. What we're going to find, if we are adding hydronium, we are adding a product. Remember, according to Le Chatelier's principle, we're going to shift to remove that added product, which means our equilibrium is going to shift in the reverse direction. We're shifting away from what we added. So if we're shifting away, we're going to use product, we're going to form reactant, which means as a result, the hydroxide concentration goes down. As a result, in an acidic solution, we're going to find that hydronium and hydroxide, first of all, are no longer equal, and they're also no longer equal to 1 times 10 to the negative 7th. We're going to find that the hydronium concentration will be greater than the hydroxide concentration. So they're both always present, but if it's an acidic solution, the hydronium concentration is greater. Now, if we have a basic solution, this is one in which the hydroxide concentration increases. So we add that base, we're producing hydroxide. Now, if the neutral solution was 1 times 10 to the negative 7th molar, and a basic solution increases the hydroxide, that means that the hydroxide concentration will now be greater than 1 times 10 to the negative 7th. Again, we're going to see an equilibrium shift. This time, we are again adding more product. We shift to remove that product, so we shift in the reverse, which uses up product, so we're going to find that hydronium goes down. So in a basic solution, the concentration of the hydronium will be less than the concentration of the hydroxide. So in terms of concentrations, if my hydronium and hydroxide concentrations are equal, we have a neutral solution. If that solution happens to be at room temperature, then their concentrations are 1 times 10 to the negative 7th molar. An acidic solution, again, is one in which we add something to water and it increases the hydronium concentration. So hydronium will be greater than 1 times 10 to the negative 7th. It will also be greater than the hydroxide. The hydroxide will be less than 1 times 10 to the negative 7th. Basic solution, it's the hydroxide concentration that is now greater. Now here we've looked at identifying acidic, basic, or neutral solutions based on concentrations of hydronium and hydroxide. Now, a more common way, or a way you've probably heard of before, is using a pH scale, which we'll look at in our next video.